I have a dream. Well, okay, I had a dream last night. But anyway, so I finished the class on discrete optimization. It was fun. It was an 8-week class. I did the final couple weeks last night, I guess. Turned in all the homework. It turned out all the problems are very similar to each other, actually. They're all based on what I said in my previous lecture. My previous video log. It's Yeah, it's basically the thing I liked about it is that it matches the way I think about problems. I stopped watching his videos. There were some errors in it that are actually fairly major. And also he was mapping everything to this mini zinc, I think it was called, language, which I never really used. So I just sat down and said, can I solve the problems on my own? And I did. It's the thing about these problems, constraint satisfaction problems and other things like that, is that it's kind of how I like to code. It's like I sit down and try something that works, kind of. It gets the basic results. Like if I open a file, it prints I call a function, it just prints the file name. Then I read the first line of the file and print that out. Then I reiterate over the file. So I do an iterative coding style rather than top down or bottom up. It's I get some stuff and then slowly increment until I have something that actually does what I want. Well, at least in a testing phase. Then once I can try out some stuff, then I go, oh, okay, here's the solution. Then if it needs to actually work in production or long term, then I can rewrite it with an understanding of what it's supposed to actually do. And that's one of the things for these kind of problems in the program, discrete optimization program that he had, was that you get a bunch of data and you say, oh, well, how would this possibly work? And it'll take longer than the time of the universe to run if you run just a full comprehensive search. So it's like, okay, well, let me try something. Okay, I got some results. Can I get better results? And just keep improving the solutions until I got within the range of passing scores. So I thought it only take me like an hour to do the last set of problems, and then I was 1 point away from passing the entire class because I needed a passing grade in each one, and I was 1 point away. And it took me like 3 hours to get that last point because I was using a stochastic or a random search because I figured, well, I'm so close, I might just let it randomly search for results and try to iteratively improve the results through randomness. It finds one. If that works, then it keeps that, and if it's not, then it moves on. And there was a bunch of other techniques I could have done to make it faster, but it was so close. I kept thinking, oh, it's so close. I just want to run this one more time, and maybe by random chance it'll find the answer that's closer. And eventually it did. So I don't know if that's cheating or not, but it's kind of what you have to do in most of these. Most of it is guided randomness. You pick a result and then say, hey, is this better than the previous one? If it is, then throw it away or keep it. Unless you're doing something like a simulated annealing, in that case, you'll randomly keep really bad results. Just move it along, but try other areas. Because I think I mentioned in one of the previous videos, most of this stuff is local search as opposed to a global search. And so in a local search, it's like there's a valley, and you're here, and you want to find the minimum point, so it's right here. Well, if you're starting this side, the same thing. The minimum point's down here. But you're in a valley. It could be at the next valley here is even much lower. So somehow you have to get from here to this one to go down to that next valley over here where maybe the global minimum is. And so you may have like a reasonable search, like if you want to try to find the minimum distance to go between 100 different cities. It's like, well, you can pick something that's really, really bad, and you say, well, okay, if I swap these two cities, it's a little closer and a little closer. And you'll never actually get with the really large ones an answer in a reasonable amount of time. Thousands of cities, you can't possibly map it all. And that's where there's millions of dollars involved. People who can come up with solutions to that are worth a lot of money, I hear. So, but the problems are there. They're interesting. They're fun. And the idea is this is an iterative approach. At least that's what I did. And I found a solution and then just kept improving it. And the reason I liked the class initially, because at first I wasn't sure about it. I was taking it with my friend Frank. And it's good. It was good to take it with somebody else. And then I realized that once I started the class, it's like, oh yeah, this is exactly the same kind of stuff that for machine learning. That it's an iterative approach. It's a gradient descent. You pick a solution, and then you come up with something slightly better. And that's pretty much all it is, right? It's not really learning anything. It's it's a huge space, and you're trying to map a set of equations to something that's reasonably close, but isn't specific enough so that other things may generally kind of be close to that in that space, will end up in the same categorization. So if you have a bunch of points clustered over here and a bunch of points clustered over here, and a new point comes along and it's over here, you say, oh, it's one of these things. If it comes along over here, you say it's one of those things. And then, but when you start off, you have no idea that there's these clusters. And so you end up trying to separate the points, and you start like this, and it's like, well, half are here and half aren't, until eventually you end up with something that actually separates those two. But then It's like, well, where does the separation line go to? It's like, well, it depends on your examples. And so it's the same kind of thing. It's trying to find a solution that you don't want to, you can't find an exact solution in a reasonable amount of time. So you have to find one that's reasonably close in a reasonable amount of time. And the one thing that I liked about this versus the other ones are big data versus small data. On machine learning, it's usually, at least nowadays, they're looking about more and more data because the algorithms are still the same as the ones from the 70s and 60s. And it's just now that they have more data, more compute power for it. So CUDA really reigns now because it's like, oh, I can just take that same old algorithm, just apply it over and over and just slowly get closer to the results, slowly go down that little dip until I find the bottom. And there's really not a lot of, at least that I read. I mean, I read all the papers and people have like minor tweaks and find some ways of momentum. Like, oh, if it's going down a hill, it's getting faster and faster, then we can kind of predict where the bottom will be. And it's things like that it seems that people have tried to do, but it's mostly big data kind of stuff. And the thing I liked about this class was that you could do it with small data. It's only a couple hundred points. And yet a couple hundred points or a couple thousand points could still take more than the time in the universe to come up with the optimal solution. Whereas in machine learning, it seems that all this stuff requires more data. If you give it a terabyte of data, billions and billions of points, then eventually it starts to get better at it and give it weeks of time or millions of years of compute power. And so it's one of the things that I kept thinking about. Well, I always think about off and on, but thinking about it more and more is that there's got to be a better way. I mean, can you do it with less information? I mean, or less data, more information. So how much information is contained within your data? Then coming with a more optimal and quicker way of coming to a solution. And it's kind of what I've always done my entire career. So it was always hard to explain to people when I tell them that I do performance work. They'd always say, oh, you rewrite stuff in assembly language. And I'm like, well, that's part of it. I can do that. And usually you can get a linear. You can make things 10 times, 100 times faster. Switch to CUDA thousands of times faster. So sure, instead of taking a week to run, you can get it in a few minutes. But something compared to the lifetime of the universe, I mean, okay, divide it by 1,000. It's still longer than you're going to be alive, probably. I don't know. Maybe you're immortal like me. But if it's, billions of years, it doesn't really matter if you divide by 1,000. Then it's millions of years. So it requires an entirely different type of algorithm, a different way of looking at the problem and coming up with a solution. And so I always try to explain to people, it's like, well, when I do performance work, I look at that first. That's why I always like programming stuff first in a high-level language. I used to use Smalltalk or something like that, but now I use Python. I think it's fairly equivalent. And the idea is that in Python, I can try algorithms very quickly without having to worry about memory management or what's in what register or how things are actually done. It really doesn't matter. I can focus just on the algorithm and say, oh, well, here's a way of doing this. This program will take longer than the lifetime of the universe, so even though Python is 300 times longer, it's like 300 times of the universe. So it doesn't really matter. You have to get it way down in time. And so mostly that's done through like pruning the tree, as that they say. It's like if you have bunch of decisions, like you can turn left and right at all these different places. So you have your spot here is where you start. And you say, okay, well, do I choose to put this item in my backpack or this item in the backpack? Then you get here, it's like, well, this item or this item. And then you work your way down. It looks like a tree. And if you, pruning the tree is you cut off branches. You say, well, if I put this item in, I can't put this in. So I don't need to check all the different possibilities. So you've cut your tree in half. It's like, great. Then if you do the same thing on the other side, you can cut it down again by half. And every time you can prune off a big branch, you can reduce the algorithm by a lot. And like 2 to the 32nd power is 4 billion something, right? So if you can divide it in half by 32, you can cut it down to 1/4 of the time. That's much greater than your 1000x. And that's what you have to do. It's called, you can change the order of the algorithm. Instead of it being x squared, or you can make it x, or x log x, or n, they say. So instead of it taking, if it's x squared, if it's 1,000 operations, then it will take 1,000 times 1,000 if it's an n squared operation. And so if it takes 1,000, if you have 1,000 pieces of data, it'll take 1,000,000 operations. If you have 10,000, it'll take 100 million, right? Yeah. And so it just goes up by a much larger factor. But if you have something that's linear and you have 100 operations or 100 pieces of data, it'll take 100 units of time. Then if you multiply it by 10, it only goes up by 10. It's only 1,000 rather than going up by 100. And so it's more of that kind of stuff. And that's what I've always tried to explain to people. It's like, yeah, okay, sure. I can rewrite stuff in assembly, and I've done that for many, many years. But I also change the order of the algorithms. I look at the stuff and say, okay, well, what if we increase our data by a certain amount? Will that make it so it's unattainable anymore? You can't get an answer. It'll take a huge amount of time longer. And there's easy ways to measure that. You feed in data, then you multiply your data by 2 or 10, or you keep feeding in twice the amount of data, and if it takes more than twice as long, then that means you have a problem with the algorithm potentially, and may not ever finish. So I look at those kind of things, because, data is what drives your code. People think, oh, it's all about code. It's like, well, optimization is mostly about analyzing data. The same with machine learning. People just think they throw their data at the machine learning algorithms and it comes up with solutions, but you really have to be able to visualize it. And that was the key to solving the discrete optimization class, was that I finally started putting all this graphing stuff in from Python. It has a bunch of libraries. And once I could see it, then I could personally say, oh, well, I can see this data isn't grouped quite right. I can fix that. And then I wrote my code to fix that. And then it made it so that it could actually run in a reasonable amount of time. And it's the same for any kind of program like that. You need to be able to, the human is the person who's doing the learning, is how I always look at it. It's like I look at it and go, oh yeah, this is what it's doing, so therefore I need to correct for that. And if you look at, data is what runs the algorithm. It's like you can say, if your data is mostly zeros, then you use this kind of algorithm. If it's mostly large numbers, then you use a different kind of algorithm. And by knowing the data, you can make your code much faster. It's just, you say, okay, well, it's going to process this way. Especially like matrix multiplies are a big one, where it's, if most of them are zero, you can use sparse matrix multiplies or things like that. So in machine learning, there's a lot of cases where you have these vast arrays, millions of entries long, and most of them are zero. And a lot of the code that doesn't think about it just will multiply them out. And 0 times anything is 0, so it's just a wasted operation. If you have a million of them and only one real piece of data, you can just keep that one piece of data and not worry about the other million. And that's exactly the same thing with this discrete optimization class, was that most of the time, most of the information was worthless. Most of the data was worthless. It had no information. It's all basically zero, or it's not possible in the solution. So by ruling all that out, you can make it faster. So yeah, anyway, so I'm done with the class. So now it's time to get to the real work, which was starting my company. I already have arcane.ai registered, and I had a website up for a bit. It just has a picture of a chimp or a monkey, a gorilla. I don't know. But anyway, yeah. Some CUDA stuff, and maybe potentially turn that into the machine learning for CUDA book. So we'll see. I have a bunch of things I'm exploring, but just wanted to keep track of all this and let everybody know that the class is over, and it was a lot of fun. I don't know, I can still go back, I guess, and try to optimize more, but my results already for the first ones that I optimized were in Python fast, just as fast or faster than a lot of the C implementations people had. So it's just a matter of knowing your data and printing properly for it. Writing your code for that, and just treating them all differently than most people, I think. The way I look at it's different than other people, because I learned right there myself. So I don't know. Yeah, I'll explain it all some other time. I'm rambling at the end of the video here, like always. So, but anyway. And the dream that I started off with. Sorry, I was going to talk about them, but then I drifted off into this. I have, like I said, weird dreams every night. But last night I had one of these dreams that I always hate, where it's I'm watching something for an infinity. So there was a person whose life I was watching on TV, and this person was an immortal, and I was like, oh, let me go back to see how it started. And the movie started showing how he lived forever, and that he didn't talk for 10,000 years, and then people were wondering what happened, and they built entire societies around him, and the dream just kept going on and on. But in part of it, there was these little things that they're like plastic looking, that were white at the bottom and blue on the top, that kind of floated in space. And they just held in space perfectly. And I realized within the dream that it wasn't like anti-gravity or anything, but it was a different technology. And I remember my alien technology video where I was saying, ooh, if I could analyze alien technology. And I thought, well, what if I can't get my hands on it? But if aliens are beaming the ideas into my head and I can analyze in my dream. Okay, that's what I was thinking when I was half asleep. But the idea being, yeah, I guess that's where science fiction ideas come from. They think of some idea when they're asleep, or think of DNA molecules, and it's when you wake up, you analyze and go, well, how would that work? And I was thinking about that today. It's like, well, how would you get something to float like that? It's like, well, maybe the rules of the universe are entirely different. That the universe is a giant calculation, and if you have some way of overflowing that calculation, you can create objects that have different sets of rules than the normal objects we have around us. So, but anyway, cool. Well, I hope you have a good one, and it's raining out there. I don't know if it is where you are, but have a great day and enjoy the weather.